Good morning and welcome to a geometry video with examples this time, not just theory anymore. Today's topic of thought is area of circle parts. Not just the whole circle, but now we're breaking it down into smaller pieces. Of course, you found from the previous section that the area of a circle itself was that mysterious and wonderful numeral pi times the radius squared, pi r squared. And if we divide the circle, if we slice it up, chop it into pieces, because of course you can't eat the whole pizza at once, right? It just won't fit in your mouth that way. You got to at least get bite-sized chunks out of it. Okay. We could use the classic pizza slice, aka a sector of a circle, okay? Or if you get the party cut, where you get it cut into tiny little, some people say, rectangle slices, right? They're going to start with these kinds of slices, and you end up with a segment. And of course, you have more overlapping segments, then you get little square chunks of pizza, right? But if you just do one slice at a time, at that point, you now have two halves of a pizza. It's a segment of the circle. And then you could, if you were to say, like, cut off all the crust. Some people don't like the crust of people. Some people really like the crust of the pizza. That's their favorite part, especially if you get the stuffed crust. Okay, and the crust of the pizza would be called an annulus. It's a really big, fancy word. And yes, the etymology is the same origin as the other word that you're probably thinking of. I'm not going to say it. It's a hole. We'll just leave it there. All right, but how do you find the area of these pieces in particular, not just the whole circle? Well, I bet, without looking at the formulas themselves, I bet we could figure this out just by using a little bit of thought and really focusing on what element we want to highlight and how that compares to the rest of the circle. What is the relationship between the part and the whole? I'm actually going to look at the annulus first. I think it's a little bit simpler. Here we have a shaded annular area, an annulus. Okay, they tell us the area already. So this is one of those working backwards kinds of problems. Let me reduce my pen size here. Oh, eraser, please. Thank you. All right. So they tell us the area is 32 pi, and that is in centimeters squared. Remember that unit for later. We're going to work backwards to find r. Now, we are given that this 18 here is the distance. Let's see, that looks like it lines up with the outside of the circle, right? And this radius, as marked, only goes to the inside of the circle. So what we're doing is we're comparing an outside circle to an inside circle. I hope that makes sense. And so the shaded region, the annulus, is in between that. So I think from looking at this, we should be able to conclude that the area of, let's call this shaded region, A for annulus. Area of A is the area of the outside minus the area of the inside. Right? So we're just going to do a simple subtraction. It is two circles, one subtracted from the other. I hope that is fairly clear. If you were to take an actual, like, say, pizza, right, and you cut around the crust and you take the middle section out, or much simpler, you could do this on a piece of paper. If you had a circular piece of paper handy, right, you could cut out the inside, remove that, and what is left is but the ring around the outside, thus giving you the area of the annulus. So we're going to make use of that to solve this slightly more complicated work backwards problem. The area of the shaded region is 32 pi. So this area is area of, I called it region A, just so we have a subscript to use. Okay. The only dimension I have is this 18. That's associated with the outside. I want to find r, which is associated with the inside. So it looks like I already have this. I can get that. And I want to find u, area of the inside. So I'm going to do a little quick algebra here. We're going to move isolate area of the inside, right? If we want that one, we could add to both sides. That would give us a sub a plus a in equals a out. But I don't want to solve for a out, so I got to subtract again to get a in all by itself. So that would be a in is equal to area of the outside circle minus the area of the annulus. All right, that's not too complicated. It's subtraction of two areas. It will get a little tricky because I do want to reduce that down to finding r, which means the area of the inside, that's a circular shape, so that's just going to be pi r square. We'll replace that there. Area of the outside, that's also a circle, so that's going to be pi, let's give it a big R square. I don't know that big R, right? That's not the thing I'm trying to find, but it's not a value they gave me either. I'll have to figure that out in a minute. Minus the area A, they gave us that. That's the 32 pi there. Okay, not bad. How about this big R? The radius for the outside circle. Well, the only thing I know about the outside circle is the 18 right there. But the 18 stretches all the way across, which means it is a diameter, right? So if I want to find the radius given the diameter, I'm going to have to divide that by 2. So real quick, 18 divided by 2 is, of course, 9. So that means this big R here, I can replace with a 9. That's not bad. Now I have a single equation. There is a single unsolved, unknown variable left, and that would be our buddy little r that we're looking for there. And everything else is just numbers. Right? It's just numbers added and subtracted. Not a problem. First thing I'm going to do, though, because we're dealing with circles, everything's got that pi in it. Oh man, pi is this irrational thing. It just keeps going on and on and on, like that teacher you know that just won't shut up. Okay? I want to get rid of it. And I can do so because every single term in this equation has a pi in it. I can divide this whole side by pi, boom, boom. I can divide this whole side by pi. Remember, each term has to do that. Technically, I would factor it out first, set it to the side, and then reduce. Okay, but everything has a pi, so we don't have to worry about it. We'll just get rid of it. To save space, I'm erasing. Please don't actually do this. Rewrite it on another line. Try to keep everything on screen here so we don't lose too much information. All right, now we know r squared is equal to 9 squared. 9 squared, 9 squared, 9 squared. I think we can do that one. That should be 81. 81 minus the 32. And that's, oh, well that's actually quite simple. We really reduced this down. 81 minus 32. Let's see, 81 minus 30 would be 51. And so 2 down from 51, 50, 49. 49. I believe the answer is 49. And by answer, I mean, of course, r squared is equal to 49. Okay, quick little mental arithmetic there. So now we don't want r squared. We want just r. So to get just r, I must undo squaring, the opposite of which is square root. So we're going to square root both sides. Square root of 49. 6 is 36. 7. 7. Square root of 49 is 7. 7 times 7 is 49. So then the inner radius must be 7. Oh, wait. One little detail there. They said the area was in centimeters squared, so the units on this must be centimeters. There. Whew. Don't want to lose that half point for the units. Radius is 7 centimeters. Not too shabby, right? Not actually as complicated as it might seem at first. Let's have a look at another one. Here we have the shaded area of, it looks like a sector. This is the slice of pizza. Okay, that's pretty cool. How do we get the area of a slice of pizza if it's not the whole thing? Well, I want you to think back of what we know about circles already, and where have we done just a section, just a part of a circle before? Before we did area, we were looking at the actual circle itself, right? Just the outside perimeter circumference edge bit, just those points there, not filling in the middle. We took a little piece of it, a chunk of it. We called that an arc, right? Arc of the circle. And its measure, if you recall, was some angle, some central angle out of 360, which gave us a fraction. How much of the circle? Whole circle is 360 degrees, so if we take that central angle, it measures about this much, right? A quarter of the circle, oh, half the circle, right? 180 out of 360 turns into a half circle. So you get this nice simplification when you're dealing with those obvious fractions that you can just look at and say, oh, that's clearly half the circle. That's a quarter of the circle. You should end up with something that intuitively feels like a quarter of the circle. This problem right here looks like not quite, a little bit less than a quarter of the circle. So we should end up with a fraction a little bit less than a quarter of the circle. Okay. Back to arc. Before we were taking x out of 360 times the circumference, right? But now we want an area. So instead of a percent or a fraction of the circumference, we're going to want a fraction of area of the whole circle. So area of the slice, the segment, the sector of the circle. I don't know why they said sector. It's just a fun word, you know? Sector. It's like, it always reminds me of space, because in Star Wars and Star Trek, they're talking about the sector of the galaxy, right? Galaxy is roughly circular in shape, so it kind of makes sense. Okay, so this sector of the galaxy, how much area is there? We already know that. They tell us the shaded area of the sector, I'm going to call it S, is 120 pi centimeters squared. They tell us the radius. Ooh, that's good. Good to know. Radius is 24 centimeters. Okay, so we know this radius. We know this area, we'll call that S. And we've worked out that the area of the sector should just be a fraction of the whole circle. What fraction? Well, it would be that x, that central angle. That's what we're trying to find. Okay, so let's put in a few things that we know here. Area S, 120 pi, will be equal to that x out of 360 times area of the whole circle, pi r square. In this case, our r is 24. We're going to have to square that. That's our setup. From there, we've already taken care of the geometry, really. That was the idea. Realize what the picture is trying to tell you, and then work out, okay, which formulas am I going to need? How do they relate to each other? Combine this, combine that. Done. Okay? Once you get down to a single formula, now it's just algebra. I have one equation. I'm solving for one variable. That's all we need. So I'm going to use the same trick as before. There's a pi on both sides. Remember, this is multiplying. So there's only one term here on the right-hand side. I got to get used to using this laser pointer more often. Okay? Only one term on the right-hand side and one term on the left. They both have pi. Let's get rid of the pi for now. Just set it aside. We'll eat it later, I'm sure. It'll be fine. Stick it in the fridge. It'll be okay. So now we're down to 120 equals x out of 360 times the 24 squared. So just isolate x. I'm not going to worry about what 24 squared is yet. I'm not going to try to work, don't start multiplying that and dealing with that. Maybe something simpler will come along and we can start reducing things before we have to mess around with multiplying larger numbers. So for example, first thing, x divided by 360. Get rid of that. Multiply both sides by 360. Okay, that takes care of this guy. And then x is now multiplied by the 24 squared. We want to undo that. Divide by 24 squared. Okay. That's not too bad. All right, now we are down to just x on one side. 360 times 120 divided by the 24 squared. If you are using a scientific or graphing calculator, you should probably be able to get away typing that in order: 360 times 120 divided by 24 squared. The order of operations should trigger the squared before the division. Most calculators nowadays will be able to handle that. I, however, am not going to use a calculator. We're going to try a little bit of mental mathematics tricks to see if we can't reduce this in our heads, or at least in our heads / on paper. I know that 360 is the same as 3 times 120, right? That's just 3 times 12 is 36, but with a 0 on the end, okay? Your multiplication table, right? You memorize that 1 through 12 all the way times 1 through 12. You got that whole thing memorized, of course, naturally, because you should have done that in grade school. If you haven't done that, you should get on that, okay? 360 is 3 times 120. Okay? Now I'm seeing a pattern here. Something should stand out to you. Hey, there's 12, there's 12. Guess what 24 is? 24 is just 2 times 12. What's squared? Ah, that means, it says squaring. Let's write that out as all the factors. 2 times 12 times 2 times 12. Okay? Guess what 120 is? 12 times 10. Okay? So, that 12 reduces with that 12. There's a 12 over 12. That's just 1. So now the 120 just becomes 10, and the 12 on the bottom, gone. This 120, boom, is now 10. This 12, gone. I'm not seeing any difficult numbers at this point. We've got a 3 on top. A couple 10s. Add some zeros to the end. Big deal. There's just 2s on the bottom, right? 2 times 2 is 4. This is now 3 times 2 zeros is 100, and divided by 4. 300 divided by 4. I think you can take care of that, right? 100 divided by 4. Actually, let's just start there. 100 divided by 4. What is 1/4 of 100? Full dollar is how many cents? Divided by 4? 25. 25. 3 times 25? You have 3/4. Well, now you got 75 cents. Okay? So should be 75. Now, before we call it done, double check units. They give us the area in centimeters. So the area in centimeters squared. So then our x should be in degrees. That's right, because we're solving for an angle. I almost got you there, didn't I? Almost got you. All right. Okay. Let's bring out the calculator just to double check, because if I was wrong on the video, that would be very embarrassing. 360 times 120 divided by 24 squared is, yes, 75. Let's see if I can get it without the glare there. 75. Perfect. See? Mental math. All right, not too bad. Obviously, if I was doing this on such an SAT or some kind of standardized test, I'd be moving a lot faster because I wouldn't be having to explain myself. But if you can practice that, you can get to the point where you see those factors and you're like, oh, that's just going to reduce to that, and that's just going to be a 2. Come on, right? Not a big deal. You don't have to reach for the calculator every time. There is one more section that I haven't covered yet. And the video is getting kind of long. How do you deal with a segment of a circle? Well, the segment of a circle is really 2 things, right? It is a sector and a triangle. Okay? If I was to take this shape outlined in purple here, that would be a sector. I need to reduce the pen thickness there a little bit. There we go. I'm so zoomed in here. That's a sector. Okay. And then let's do another color. In green, here we have, of course, a triangle. So if you take the sector and you subtract the triangle, what is left is going to be just the segment of the circle. Now, in certain scenarios, they are, of course, going to need to give you all of the information, so be careful, analyze the problem, make sure you have everything you need. For the sector, you're going to need, I gotta pause for tea. Okay, there, let's finish this up. For the sector, you're going to need the central angle, so you know what fraction of the whole, right? And you're going to need the radius. Of course, because we're dealing with circles here. You gotta have the radius, right? In order to get the area. Talking about going forwards from information to find area. Of course, the problems we did, we worked backwards, because those are usually the more difficult ones for some students. The other thing to look at is then the triangle. What do I need in order to solve for the triangle? I'm going to need the triangle base and height. One of these things will be the radius. Okay? Which one? It depends on exactly how you're labeling them. In my diagram, I would probably say, call this, use the laser pointer again, right? Let's call this section the base, which means our height would have to be something in like that, right? To be perpendicular. So we would need to be given that distance, right? The height of this triangle in here. They might instead give you something that is more like that, okay? And this is a part of a radius. It would keep going. But the advantage there, zoom in even more zoom, enhance, right? Is it is perpendicular to this segment, boom, which we of course know is the chord of the circle, right? So they could give you those two, and that would function as a base and a height, in which case neither of them was the radius of the circle. Okay? Depends on what they give you. Can be the radius. Sometimes you get that double overlap, but they might give you the chord and piece of a radius instead. Okay? So that's dealing with a segment. We covered annulus. We covered sectors. We covered segments. Briefly. We went backwards. We did some mental math. Oh my goodness, what an action-packed video this has been. I hope it's been most helpful for you. It's been a blast for me. Come back next time. We'll do, next thing that pops up and seems confusing. Let me know if you have any questions. You can email me, put them on Google Classroom, or those of you not in my class but on internet land, please leave a comment below. Maybe I'd be happy to cover another topic over the weekend. So, thank you so much for watching. So long, farewell, enjoy the rest of your day.